Okay, maybe let's get started.
Okay, sure.
Okay, good afternoon, everyone. Thank you for joining us today. And it's my great pleasure to introduce our speaker, Professor Nandita Vajakumar. Nandita's PhD advisor was also my postdoc advisor. That's how we came to meet each other. And Nandita is an assistant professor in the Department of Computer Science at the University of Toronto, where she leads the Embark Research Group. She's also a faculty member at the Vector Institute for Artificial Intelligence and a research scholar at Amazon. Her research lies at the intersection of the computer system and architecture, visual computing, robotics, machine learning. In particular, she develops the efficient, scalable, and programmable system that enables machines to perceive, interact, and interact with the physical world. Please join me in giving a warm welcome to Nandita.
Thank you for the intro, Hayu. So it's really nice to be here to talk about some of my group's recent research. So we do research at the intersection of computer systems and domains like computer vision and robotics. So in this talk, I'll try to connect these two areas with some of our recent works. So let's get started. By the way, feel free to stop me at any time if we have questions. I'm going to cover a whole bunch of different topics. So I'm happy to take any clarification questions right in the middle as well. So we can turn it into more of an interactive session if you have any questions. All right, so let's get started. So an important new frontier today is how do we actually leverage our advances in machine learning and AI to actually help machines understand and interact with the physical world, right? So very often, the mile-high view of some of the building blocks that is involved in this process may look something like this, where we start with some sensors that try to capture some information about the surroundings. And this could be just cameras, but it could also be other types of sensors, for example, GPS and so on. And then we may try to extract some meaningful information from them with various perception tasks. And this includes things like object tracking, segmentation, etc. And many downstream applications involve building some kind of representation of the environment. And this could be either a 3D model or a latent vector or some kind of map of the environment. And then finally, we can do some useful tasks. And this ranges from different things, for example, interacting or navigating the environment, the way that, for example, a robot or a self-driving car may do, or it could be inverse rendering, which I'll talk about in a little bit, or it could be generating entirely new content. And we'll go over all of these later in this talk. So these are key building blocks of many important applications today. For example, everything from autonomous driving to robotics to physics simulation to AR, VR, content creation. So this application space is quite broad. And they all have in common that these are applications that involve in some way modeling and interacting with the physical world. So here is an outline of what I'll try to cover in today's talk. So first, I'll give you some background of some of the tasks in this space, and I'll try to motivate this application space a little bit, and hopefully also convey what the transformative advances are in this space recently. And then we'll talk about some of the system level challenges when it comes to building systems to support these applications. And I'll talk about what our challenge, how we address some of these challenges in our recent research. And finally, if we have time, I'll also talk about some of the algorithmic aspects of our research, which is more on how do we actually enable the latest developments in the algorithm side. That won't be the focus of the talk, but I'll just give you a little bit of an overview of this. And finally, I'll end with the bigger picture and some takeaways. Okay, so 3D reconstruction is a very fundamental building block in many of these applications. So what this involves is starting with some sensors. We are trying to build a 3D representation of the environment in various formats, for example, point clouds or meshes and other types, more recently, neural representations as well. And these 3D data structures are really at the heart of spatial understanding. And there are many system level challenges that arise from this, and I'll talk about what they are later in this talk. So inverse rendering is another foundational task in this space. And the goal of this task is starting from images and videos. We try to recover information about the surroundings that were captured in those images. For example, the materials of surfaces, the shapes of various objects and the environment, lighting conditions, and so on. So here's an example from some of our recent work, which is actually state of art in this space, where starting from an input video, that's all we have, we can directly extract, I'm sorry that the videos are not showing up that smoothly, but you can see that we're trying to extract information like the shapes of the surfaces, which is the surface normals, the depth, right, how far the various surfaces are from the camera, and other properties of the surfaces. For example, the colors, how metallic the surfaces are, how rough the surfaces are, and so on. So this is inverse rendering. So we were able to do all of this just from an input video. So I'll talk about how we actually did this towards the end of the talk, but it won't be really a focus of this particular talk. So why is all of this interesting? So beyond just understanding the world from sensory data, it also allows us to create new imagery and videos as well. And this is very important for things like simulations, for robotics, self-driving, content creation. And many of us have actually used a lot of these various applications today. So this could involve generating entirely new visual content or editing them in some form. And here are some examples also from our recent work. So another task is relighting, where the goal over here is to change the lighting conditions in any video, right? And an environment map represents the visual surroundings, basically the lighting conditions as well as the environment around. And the idea is that a different environment map means that you have different lighting conditions you want in the video. So here are some results from one of our recent works at CVPR, where we are actually able to change the lighting conditions on a video. And this is actually quite a challenging task. And the reason for this is that the shadowing needs to be accurate. And also all of the coloring, all of this. So to get this looking very photorealistic is actually quite challenging, but we're able to do it quite well today. So where is something like relighting actually used? So here's an example of relighting. And this is in self-driving, where we may want to create a lot more environments under different scenarios to help train cars, for example, self-driving cars and robots as well. So this is a use case for relighting videos. Another use case is object insertion. So over here, we're basically trying to insert objects into images in a very photorealistic way. And the reason that this is quite challenging is because we want the shadowing and the other aspects of the scene to look very realistic. So this is actually a very challenging task, but as you can see, it looks reasonably photorealistic here and quite accurate. And again, this is useful for a range of different tasks like editing existing images and videos, creating new content, and many others. And this was an example from our recent works at NeurIPS. So going back to the building blocks over here, so many of these building blocks are quite traditional, but what are some of the transformative advances in this space? So first of all, we have much richer sensors now that enable us to do a lot more. For example, event cameras, which I'll talk about a little bit later in this talk, but they allow you to capture a lot richer information, which allows you to do more. And the second transformation is that now we are moving away from traditional 3D representations like meshes and point clouds and so on, and more towards data-driven representations like NeurIPS and 3D Gaussians, where they're effectively just learned in a manner very similar to a neural network directly from data. And I'll talk a little bit about this later in this talk. And finally, we're moving away from traditional graphics pipelines towards using generative models for everything, for example, diffusion models. And these are effectively just replacing, in many cases, the rendering pipeline. And I'll talk about what the implications are as well. Shall I remove this somehow so that this isn't, yeah. Let me, minimize it. How do I do this? It's not letting me, maybe because it's recording in some manner. No, so do you see it's sort of just very strange?
Oh, okay. That's because it's the mouse is actually here.
Oh, how did that happen?
Because that's actually two screens. Right?
Oh,
Just move it here. So
I see. Perfect. Thank you. All right, this is much better. All right, now that we've discussed some of the very exciting advances, which have unlocked many exciting capabilities in this space and have made this area actually quite exciting to work on. The problem, though, is that to support these applications and to build systems that can provide the compute for them still poses many challenges. So let's discuss some of them at this point. There we go. So let's start with the challenges when it comes to the compute. So a lot of these applications are actually very amenable towards running them on GPUs. They're very parallel, so people use GPUs for this primarily. But one of the challenges is that a lot of them involve using some kind of model of the environment that they're constantly updating. And this can cause some challenges. For example, when you're dealing with shared parameters, you can have synchronization problems, which I'll discuss in a second. And with these applications, with visual data, it is extremely important to leverage sparsity and redundancy because a lot of this input data is highly redundant and there's a lot of it. So you really have to make it a first order optimization concern to leverage all of this. And a lot of these applications involve interacting with the environment. And the second you do this, you have a lot of irregularity in the compute. And this poses some challenges as well. So let me now give you some examples of each of these. Let's start with the first one. So a good example of the first one is in 3D reconstruction. And here, recall that the goal is to construct some kind of 3D representation of the environment that is highly photorealistic. So just starting with some images of a scene from various perspectives, we can build a 3D model of it that can be queried and navigated, and it looks highly photorealistic, as you can see over here. So the state of art in this space is that now we can do this in a very data-driven way. In other words, that this model is effectively just a bunch of parameters that are trained in a manner that's very similar to a neural network. And this process is called differentiable rendering. So let's talk about what differentiable rendering actually looks like. So we start with some randomly initialized weights or parameters, which is intended to be the model. So the thing to keep in mind is that each model represents only one scene. It is just a representation of the environment. So you need a new model for every scene, and it's just a small model, not like a large neural network. So you randomly initialize it, and then the input to it will be a camera angle, from which point of view are you viewing the scene, and the renderer will produce some noisy image because your weights were completely random. And then you compare it to the ground truth image, which you have from that same angle, calculate a loss, and then you update the weights using SGD, very similar to a neural network. So you keep doing this from different angles of the same scene, right? And you provide as input different angles or camera poses. And you do the same loss computation and gradient updates. And you keep doing this until the model has learned to represent that scene. Does that make sense? And at that point, you can now query this model to render a scene from any angle, and it will produce a very photorealistic image of that scene from that angle. And the nice thing about this is that this can be done entirely just from taking a bunch of pictures, which you can do on your phone, and just training this network to represent the scene. And after that, you can query it from a new angle, which you had never taken a picture of, and it will actually produce an image of that viewpoint also. And this is called novel view synthesis. Yeah. Yeah.
Is it able to do it?
No. So this is what the example I've given you here is just for static 3D. So it's like taking a picture, right? Except that this is a 3D capture. So it can represent it in all scenes. But you can extend it to 4D. So that exists also. There's another time dimension where it captures, it's like a video, but in 3D. So you can just think of it as another representation, basically. So, but that's a good question. This one does not capture change in anything, so it's static. But you can extend it to 4D, and then you can capture it. But you need more data for that at different timestamps, what it looks like. So now you have a bunch of weights that have effectively just representing that scene, right? So this is what 3D reconstruction actually is. So now let's talk a little bit about what these weights actually look like, those learned parameters. And there are many different ways to construct them. And the most popular one today is something called with Gaussians. So what this means are those parameters are basically structured as 3D Gaussian density functions. So a 2D Gaussian density function would look something like this, and this is what it would look like in 3D. And each of these Gaussian density functions has associated with it some parameters. For example, the position, where it's located in 3D, its shape, its opacity, and its color, right? And all of these parameters are trained with the process I just showed you until it represents the scene. And if you have enough of these Gaussians, then you have high representation quality, and you can represent the scene with very high fidelity. And the more of these parameters that you have, the better your representation quality. Does that make sense? So these are randomly initialized, just like I mentioned before, and then trained via SGD. So let's talk about the differentiable rendering process with the 3D Gaussians. So these randomly initialized parameters, you query, the inputs to these are the viewpoint, and then you use a standard rasterization pipeline to convert it into an image. And then you're going to compare that to the ground truth image, and then calculate the rendering loss, calculate gradients, and then you're going to go and update these weights. Right? So this is how you do the training, or what we call 3D reconstruction, essentially. So what we found in our analysis is that the backward pass is actually more than 10x slower than the forward pass. So why does this actually happen? So taking a closer look, we found that this is because of how the gradient computation is actually mapped onto the GPU and how it's actually parallelized. So typically in graphics pipeline, one of the common ways to parallelize computation is across pixels. And then each thread calculates the pixel, the loss for each pixel independently. So this is how we parallelize. And then each of these threads also computes the gradients for each pixel separately. But the problem is that, as you can see over here, each Gaussian affects, I don't know why one color is not showing up. It's quite strange, but it's a different color on my slides here, but hopefully you can still see it. Anyway, so there's, as you can see, the gradients, they affect this part. So each Gaussian effectively affects a set of different pixels. And what this means is that you have multiple gradients that are computed, but all of them are used to update the same same Gaussian or the same set of parameters. And what this means is that you have to do this in a way that they don't overwrite each other, that you have to add these gradients together before you can update the Gaussian. And if you're doing this in parallel, then this has to be done with an atomic operation, which prevents these threads from overwriting each other when they are aggregated together. Does this make sense? So GPUs provide atomic operations, so you can do this just like most compute hardware. But the problem is, in this case, there are so many of them. And this means that we're dealing with so many atomics because there are just millions of them. And to understand why atomics are actually quite slow and inefficient in GPUs, here's just a primer of how GPUs work. I apologize if this is something you already know. So any GPU comprises of a bunch of large cores called streaming multiprocessors, which in turn contain some subcores. And then outside of these subcores, we have the L2 that is shared across them, the L2 cache. And then any application is parallelized across an abstraction called thread blocks. Basically, any kernel is divided into thread blocks, and one thread block is scheduled at a single SM. And each thread block is further divided into a set of 32 wide warps, which are effectively just a set of threads that are executed together in lockstep at one of these subcores. So this is effectively how we parallelize. And the way that atomic operations are handled is that they're actually handled at the L2 with specialized hardware over there. And the reason why it is at the L2 is because it is the first shared level of the cache. So you may have to aggregate updates from across different SMs, threads in different SMs. So for that reason, it needs to be at the L2. The problem, though, is that the number of atomic units and the atomic throughput that you have is significantly lower than that of the GPU. So that means that the vast majority of the time, the cores are actually just stalled, waiting for these atomic units. And this leads to the huge bottleneck that we see with these applications. So the observation that we made to solve this is that it is extremely likely for I apologize again, the color is really not showing up, but it is extremely likely that any Gaussian maps to a nearby set of pixels, as you can see, kind of see here. And any nearby set of pixels are mapped to nearby sets of threads. And what do nearby sets of threads mean? Effectively, threads within a same warp. So what this means is that most of the time, the threads within the same warp, are updating the same Gaussian, or they're updating the same memory location, in other words. So this is something that we term intra-warp atomic locality, and we try to leverage this. So this doesn't happen all the time, but it happens a vast majority of the time. So leveraging this, the first idea that we had was, instead of sending one atomic request for every single thread, what we do is we do some atomic reduction in the core itself. For example, within the warp, we can reduce across all 32 threads. And then for each warp, we only send one atomic update to the L2. The reduction is already partially performed at the core with the various threads within a single warp. And this can significantly reduce the intra-warp atomic locality. Sorry, leverage the intra-warp atomic locality to reduce the amount of contention that you have for the atomic units. But this is not that straightforward. And the reason that we don't already do this in GPUs is because in many cases like this one, it's not that all threads in the warp always update the same memory location. That happens a lot of the time, but in many cases, you'll see something like this, where some threads are inactive or they're updating a different memory location. So there is this irregularity. So it's not that easy to directly just do this reduction. So that is the hard part over here. The second challenge is that if you do a lot of the offload to the atomic units, then if you move the atomic computation to the cores, then all of a sudden now the bottleneck shifts to the cores instead of the atomic units. And then we have an imbalance of it there. So this is also something that we have to balance, where we use both the atomic units at the L2 as well as the core. So we built a primitive that's hardware software to actually do this. And the idea is quite simple, where we implement a partial reduction using a mask within the core itself. And then we have a scheduler that decides whether it should be done in the L2 or in the core itself. So we created this reduction unit such that you can choose which threads are actually reduced together, and you can provide it a mask so we can handle the irregularity, and we can do this very efficiently. So I'm not going to go into too many details about how this was implemented, but I'm happy to answer questions on that. But I will go into some of the results and the evaluation of the performance with this. So you can actually do this in software, and we did build libraries for this, but you won't get all of the benefits of it. You'll get some benefits, and I'll show you the difference. And we evaluated the hardware-software primitive in simulators, and these are some standard applications and data sets. And here are some results in software, just using only the software version. On the x-axis are various 3D reconstruction benchmarks that we commonly use. And on the y-axis is speed up normalized to the baseline. And we find that in general, we can get some pretty significant speed ups. And the more complex the scene is, the speed ups are effectively much higher. So if we look at the results in hardware, then we can do even better than the software version. And this is because we can do the balancing, and then we can do things a lot more efficiently. And here I'm also comparing with another version which does the reduction in a slightly different way. That's prior work, but we do much better than that as well. So before I go to the next part of the talk, is there any questions on this part of it? You can ask me later as well. Okay. So now let me very briefly talk about another challenge, which is interacting with the environment, which creates some scheduling issues. So we actually see this in many different applications, but I'm going to discuss it in the point of view of physical simulations over here. So we use physical simulations quite a bit for robotics, where we effectively use it to collect data to train robots, because you don't want to train them in real environments. So we use physics simulations where you can test out various different strategies without breaking the robot. And these also use GPUs for execution because they are largely parallel. But the characteristic of these applications is that the compute really just depends on the interactions in the environment, right? Depending on what actually happens. So you don't know ahead of time exactly what compute you're going to perform. So they typically have a characteristic like this, where the kernels launched and their dependencies are actually determined only at runtime. So for a certain input, you may have kernels that are launched in a certain order. And for a different input, you could have a completely different set of orderings as well as dependencies between them. And physics simulations are one example of where we have this, where the compute graph is input dependent. But we also see this in other applications as well. For example, dynamically routed neural networks. So we see this in computer vision, where we use DNNs for various tasks. In some cases, you can actually exit early if, for example, the task was very simple, like an image recognition. It's very clear what the image is. You don't have to go through the whole neural network. And then there are other types of specialized networks that also do different things depending on the input. It's like a small version of our mixture of experts sort of model. These are very common in computer vision. And they also have the same issue, where the compute graph really just depends on the input. So the problem with these is that it can actually be quite hard to parallelize and schedule them on a GPU. So we cannot just serially execute these kernels one after the other, because if we did that, the GPU utilization would be very low, because they're all very short-running kernels. They don't really take up the full GPU. So we really have to parallelize across these kernels, not just within them. If we want to use these kernels, use the GPU well. And also, a lot of these kernels can be parallelized because they're independent. So we should really do that for efficiency. So there are different mechanisms in which we could parallelize. For example, CUDA stream is a way that you can do this, where you can launch kernels across different streams, and they'll be scheduled concurrently on the GPU. But the problem is, in these cases, we don't know these dependencies ahead of time, which means that you can only schedule them onto these streams at runtime. And this means you need to effectively coordinate with the CPU at runtime before you can launch them on these separate CUDA streams. And this can incur the latency of the CPU-GPU synchronization, which can be quite significant. And it could also, and then it would lead to stalls as well. So especially given that these are not super long-running applications, like all these can add significant latencies to the overall inference runtime. So there are other mechanisms for this. For example, CUDA graph and AMD ATMI and so on allow you to construct a DAG ahead of time and then just launch it at the CPU, where you basically tell it what's independent. But the problem is, in this case, you have to do this for every input. And the overheads of doing these compilation and scheduling of graphs for every single input is significant. So you're going to take at least half your time just doing this. So it's not really possible to do this. So what this means is that we need a new type of approach to do this scheduling when it comes to input-dependent kernels. So the idea that we came up with was to do the scheduling entirely on the GPU at runtime with a process that is similar to out-of-order execution in CPUs. So the idea is something like this, where the CPU just launches a sequence of kernels, one after the other, and the GPU looks at a window, very similar to a scheduling window in CPUs for instruction scheduling. And then within this window, let's assume that we know the dependencies between them because we provided it to the GPU, and I'll explain what information we provided. But the GPU itself tracks at runtime which kernel is executing and which kernels are dependent on it. So that way, once a kernel completes execution, the GPU itself will decide now which kernels it can release for execution. And this is very similar to how instructions are actually scheduled, right? And the key over here is providing it the right dependency information so that it can do this tracking. And the way that we do this is that kernels can be, we can say that they're dependent on each other if there's an overlap of read and write sets, right? If some kernel writes to a memory location and the next kernel reads from it, then there is a dependency. We can say that. So what we can do is at launch time, we can specify the memory ranges for each kernel that they're reading and writing. And whenever there is an overlap of these read and write sets, then we know that they are dependent on each other. So this is the extra metadata that we provide the GPU. So the range of read and write sets for each of the different kernels, and then the GPU can figure out where the dependencies are at runtime. So there's a lot more to making this work quite efficiently, but I'm not going to go into too many details, but it's all there in the paper. So here are some results that we collected from this. And since this is a hardware change, this was done on a simulator, and we did this for both physics simulations as well as some dynamic DNNs, which are, again, input dependent. And here are some results. So these are for the different workloads and normalized to the baseline speedups. So higher is better. And as you can see over here, just from fixing this, we were able to get some pretty significant speedups. So the amount of speedup that you get really depends on how much we're able to increase the utilization of the GPU. And as you can see here, we were able to increase it quite a bit. There is still quite a bit of underutilized kernels here, but that's more just fundamentally how much parallelism there is in these workloads. But there's still room for improvement over here. So any questions with this part before I quickly move on to the next one? OK, since we're running out of time a little bit, I'm going to just briefly talk about some of these next few ones. And I'm happy to chat more in detail if there's something that you're interested in. So another example I want to talk about is with sparsity. So this is something we've done quite a bit of work on, but the example I'm going to give you is demonstrate some of the changes in this area that motivates a new design. And one of it is, a good example is with high frame rate perception. So perception is actually, So perception is a task that's very commonly used today for things like object tracking, optical flow, which gathers information about changes in the environment and motion. Depth estimation, for example. And today we use CNNs or other types of neural networks for this primarily. And a challenge over here is that these are real-time applications. In other words, we want to do this at the speed at which frames are coming in. And this is very important for real-time applications. So one of the challenges with this is that new types of sensors actually have much higher frame rates. So an example of this is an event camera. So it's a different type of sensors which effectively captures the change in intensity of light at any pixels instead of just taking a snapshot. And it generates an event packet each time there is a change. So it will only generate one packet per pixel every time there is a change in intensity beyond a certain threshold. And the benefit of this is that the readout rate is very, very high, much higher than a standard camera. So it is very useful for tasks like, for example, in high moving objects like drones, where a standard camera simply cannot keep up with the changes in the environment, where it's too fast. Or when the range of light is much higher than what a standard camera can actually take. These are cases when these sensors are very useful. But the problem with this is that because you have such a high readout rate, if you want to really leverage the benefit of these kind of cameras, you need to be able to process and put them through the neural network at the same rate at which you're generating the sensory data. And that is not possible today because there's just too much compute to be able to serve this throughput. So how do we actually address this? So the key observation that we made over here is that there is a lot of sparsity in the inputs. So we're doing a lot of redundant work. But a lot of the sparsity actually is in the temporal direction, where, so before we actually feed it to the CNN, we actually compress these events into a frame, and but it's at a much higher frame rate. So what we found is that the difference between two consecutive frames is a very sparse tensor. And this is because at such high frame rates, the frames don't change that much. So it looks very similar. And the difference between them is very sparse. It's mostly zeros, right? So, and this is something we can actually leverage. And the benefit of looking at it this way as the difference between these two is that it allows us to, first of all, even deal with the types of irregular sparsity that other types of sparse applications don't. So the key idea over here, then, is to perform the inference on the difference between two consecutive frames rather than just the input itself. So the idea is something like this. So instead of feeding in the input image or frame into the neural network, we feed in the difference between two consecutive frames. And the output is also the difference between two consecutive outputs. So to get the real output, you have to add the previous output to the output increment, and then you'll get your new output. And this new output will be the previous output for the next frame, and so on. And obviously, we have to change the neural network math to actually compute on the difference rather than the actual input itself. So this is quite trivial for the linear layers, but for the nonlinear layers, there are some tricks we had to use to actually make this work, but I can explain that if you're interested in it. But by doing this now, we can significantly reduce the amount of computation by using various techniques to remove the sparsity, which is a lot more in this case. Yeah?
The camera because it's so sparse.
Uh-huh.
And then SNN is really good for processing the type of processing that is really have high sparsity. So how do you compare these method with the SNN method?
The SNN is which one again? Oh, okay, the event-driven one. Yeah, that's a great question. So the downside of the spiking neural network is that, first of all, they don't have the same accuracy as the standard CNNs. So the problem is that most neural networks today are trained with images, and they have the highest accuracy for all of these different tasks. So if you want to use a completely different neural network just for the event cameras, then you have to collect enough data to basically retrain all of them. So they don't have the same level of accuracy as the image ones, basically. So people are still working on improving that, but there's still always a gap, and you'd have to do this for every new task. You can't just use the image one. So that's the main thing. So the state of art, I believe, is still using the standard ones. Yeah. But that and the other issue with the spiking neural network is, I don't know if this has been fixed yet, but it's quite challenging to map them to hardware, like GPUs and so on. I think with like the neuromorphic style architectures and other hardware that's really defined for these event cameras, then I think those would be a good fit. But that's a great point. Yeah. Mm-hmm.
Because spiking neural network is naturally asynchronous.
Yeah.
DVS is also naturally asynchronous.
Mm-hmm.
So they directly process on the differences. But for now, we are talking about the tensors per frame. So are you like rearranging them into?
Yes, yeah. Yes, exactly. So to make it work with a standard neural network, you have to convert it back into a frame. But you'll get the frames at much higher readout rates, frame rates than a standard camera. But there are frames, yeah.
Does that mean?
I don't think so. So this is done quite efficiently directly. You can even do it on the chip, basically. So that one isn't such a big deal. Sure. These are great questions. Okay, so yeah, so there's a lot into making this actually work very generally. And this also, I think at the same time, people also propose the same idea for videos. So this would also just work for any standard images. But this is another way to think about how to do this. And every n frames or so, we'll just fall back to using just the full frame, just to avoid like the errors that may accumulate. So that's something that we also have to do. All right, so I'm going to now just go more briefly into various things. I want to talk a little bit about memory at this point. So the challenges with memory really come from the fact that we have this model or map representation, and these can cause some challenges. And I'll give you some examples of this just in the time that we have. So the first one is that they can be quite irregular in terms of how they're structured. And an example of this is in online mapping. So this is a task where we're trying to create some kind of map of the environment as we move through it, the way that a robot or a drone might, right? Like when it's navigating an unseen environment. So in this case, we would be constructing this map, for example, for navigation, for collision detection, and so on. And we're constantly processing sensory data. This could be LiDAR, this could be camera, and then we're converting it into some kind of map. So we know what is in the surroundings, and we can do navigation as per that. So the representation of the map is in the form of a voxel grid, where very often, and this is a common representation. So you can think of a voxel grid as just discretizing 3D space into a 3D set of voxels. So in 2D, it would look like this, and in 3D, it would look like this. And each of these voxels contains some local information about that point in space. And it could be something simple. For example, is that point in space occupied or not? So this is an occupancy grid over here, which tells you which point in space it was occupied by some object and which was not. But it can also have more interesting information. For example, sign distance field could be stored there instead, which tells you how far that point in space is to the closest surface. So you can have something like this as well. But either way, they're still structured as this 3D grid where each voxel maps to a 3D point in space. So what we found is that map update latencies are quite significant in these mapping applications. And they don't scale very well either. So on the x-axis, we have different mapping applications. And now we have maps of different resolutions. So here are 3 different resolutions of the map. And on the y-axis, I'm just showing you the latency of updating the map. And we found that the latency increases by 10x when we just triple the resolution. And resolution is great because it gives you more fine-grained information about your surroundings. So let's talk about what the problem with these data structures is. So we can't actually store a voxel grid as a 3D array because that would be very memory inefficient. If you look at around us, most of space is actually empty. So we shouldn't really be storing so many zeros. So instead, what we do is we use dynamic data structures like hash tables or octrees, where the input would be the XYZ coordinate and the output would be the voxel data, either the occupancy or the SDF information. This way we avoid storing a lot of zeros in the map. But the challenge is that indexing these dynamic data structures is extremely inefficient. So just a quick review of why. So for example, with the hash tables, you have to do this hash function computation. The input would be the XYZ coordinate. You have to calculate the hash function, and then you have to do this bucket traversal. It's quite a bit of pointer chasing. And for octrees, the same thing again. You have to traverse the whole tree, lots of pointer chasing in order to find the voxel information. And all of this is just slow. So the problem with these mapping applications is that for every time you capture information about the surroundings, which you constantly do, you update the map. You get some information, you update the map. You keep doing this as the robot moves. So each time we update the map, you have to make a large number of accesses to the voxels. So it's in the order of millions over here. So if you combine the large number of accesses with this indexing latency, very quickly, these access times become a huge bottleneck. And we found that about 40% of the time is actually just spent retrieving voxel data, doing this indexing, which is quite a lot. So how do we actually address this? So an observation that we made was that even though we're making millions of accesses to voxels, most of these accesses are to the same set of about a few hundred at any given time. There's a lot of locality in the accesses that we make. And this makes sense because if you think about it, as we're usually updating one part of the map at any given time as the robot is moving, right? And you're constantly going to be updating the same until we get to a different location. So that sort of makes sense. So the key idea over here is that to address this indexing latency is that instead of doing this indexing for each one, for every single XYZ coordinate, we actually just cache the most recently used mappings between the XYZ coordinate and the block pointer with the voxel data. So to be clear, we're not caching the data that's already in the cache. The caches are working. What we're caching is the mapping between the XYZ coordinate and the block pointer, so that we don't have to keep doing this hash table computation, hash function computation, or this octree traversal. So that's exactly what it saves us. And we call this cache the voxel cache. And we can actually use the L1 cache or the L2 cache itself to store this voxel cache. Or you can do it in software, but this is a hardware proposal where we add 2 new instructions which allow you to look up the voxel cache to see if the mapping was already there, if that XYZ coordinate was there, and if not, actually add it into it. And I'm not going to go into too many details about how we did this, but it can be done quite efficiently, and we can use existing caches here. You can save away in the existing caches in order to do this. Lots of details in the paper about how this can be done efficiently. And here are some results on both CPUs and GPUs for common mapping. And these were done in simulation, and these are for 3 different resolutions of the map. X-axis are various mapping applications, and this is speed up normalized to the baseline. As you can see over here, just by fixing this, you can get speed ups that are quite significant on CPUs and also even higher on GPUs. Okay, so I just want to briefly go over some other problems here without going into too many details before I end, but any questions on this part? I think we have about 5 minutes left. Okay. All right, so let me briefly talk about memory capacity, which is a significant challenge with many of these workloads. And the reason for this is that the representation quality very often has to do with how much memory you can use to store these parameters. So I'm not sure if it's visible over here because for some reason things are not showing up great, but if you use 100K Gaussians, you can see a lot of artifacts and it's a bit more blurry. Whereas if you use millions of Gaussians, it's a lot more crisp and it can capture a lot more detail. So basically, if you have more parameters, we can represent 3D in a much better way. But the problem is that these Gaussians and these parameters, they just take a lot of memory. So here are just for small scenes where a few million Gaussians is not that much, but still in order to do the reconstruction, the training, you still need something like 18 gigabytes of memory almost. And the static weights itself is still taking up so much memory. So this is significant. So imagine you need like a big GPU just to train this. A lot of these applications are intended to be mobile. That's something you want to do on your phone. So it's memory is really the key limiter to these sort of applications. And these are just small scenes. What if we want to do large scenes, like city scale scenes, for example, and represent them in 3D, which people do now? How do we actually address this? So of course, in systems, we always use compression as a way to do it. And we didn't propose this. This is actually how this can be easily done. And there are many different ways to compress, but a very straightforward one over here, again, the color seems to be disappeared, but hopefully you can see. The idea over here is that there's a lot of redundancy among the Gaussians. For example, many of them may have the same colors, they may have the same orientation. So you don't have to store millions of the same colors. So what you can do instead is just save the common parameter values, each for a different set for colors, different set for orientation, and then just store a mapping from the Gaussian to one of those, which we're going to call features in a, or feature vectors in a code book. So this way, we're only storing the common ones. We're not storing all of it. And this can remove a lot of the redundancy over here. And this is called codebook compression, which is commonly used. So that's what I'm showing you over here. And we have a code book for each of the different parameters. And then each Gaussian is just mapped into one of these. So the challenge with this is that you can do this offline once you've trained the model. But you still need all of this memory during the training process. So how do we actually do this? And this is primarily what we did in our recent work at ICCV. We enabled training on a compressed representation itself. So this cannot be done with SGD because it requires everything to be differentiable, but mappings between the code book and the Gaussians are not differentiable. They're just mappings, right? Like in indices. So how do we actually do this? I'm not going to go into too many details, but this is something that we solved as well. All right, so I'm just going to skip this part, but I will just give you a brief idea of how we actually did a lot of the things I showed you ahead of time. So one of the biggest advances over here is that traditional pipelines for rendering and inverse rendering are now being fully replaced by generative models, for example, diffusion models. I'm sure many of you are familiar with them and have used them. And we've done a lot of work in this space, a lot of it state of art in terms of how to use generative models for rendering and inverse rendering. But the idea effectively is this. So in traditional rendering and inverse rendering, we try to model how light interacts with objects and materials in a scene. And this is how we generate very realistic images and scenes. But generative models have turned this into a process where they've learned data distributions. And they've learned the distribution of realistic images. So our goal over here is to leverage these priors in these generative models and move it from, like simulating the physics of how light interacts with environments into sampling from a distribution effectively. So that's the goal of this. And this process would be entirely data-driven. So here's how we would do inverse rendering. Starting with input video, we'd want to essentially extract these material and geometry properties. And then let's say we wanted to change the environment lighting. We would use a forward renderer to get a new output video. So what we did was we replaced this inverse renderer with effectively a diffusion model. And with different conditioning, it gives you a different G buffer, basically all of the properties that I showed you before for inverse rendering. And we fine-tune this diffusion model to do this by just generating a lot of synthetic data. So we created a big data set of synthetic data and then used it to train the diffusion models. And by doing this, we were able to get it to, same thing with the forward rendering, where we effectively fine-tune a diffusion model to be able to take in as input the environment map as well as these G buffers, and then construct a new output video. So again, this was all trained with synthetically generated data. And here are some of the results from this work, actually. So by just doing this, we can get some very photorealistic results, which was traditionally a very hard task. So the top is effectively the shape, the depth, the base is the color, properties of the surface. And it can also be used for relighting, the same way as you can see over here. These are some of the results. Also for object insertion and things like this. All of this was just done entirely with generative models. All right, so some takeaways. So I hope I convinced you that this whole field, enabling machines to interact with the physical world, is an exciting next frontier. And algorithms are increasingly becoming data-driven, richer sensors, more of the learned representation, differentiable pipelines, using generative models in many different tasks, also in robotics, even though this was not a part of this talk. And these applications are really severely constrained by underlying compute systems and the programming frameworks. And really building these systems are quite crucial to advances in the field. And most of these challenges come from mismatches in abstraction between the algorithm and the underlying system. And this includes, for example, sparse computation, compressed representation, synchronization, which can cause issues with irregularity. And also, a lot of these applications are very dynamic. As I showed you, it can lead to issues with scheduling. And we found that making just small changes can fix this mismatch and give you real gains just with the existing systems that we had. So I'll end there, and this is my research group who did all this amazing work, and I'm happy to take any questions if you have at this point. Yeah.
I think that a lot of work being done on the 2D pictures or videos.
Yes.
But nowadays we already have like 3D cameras and different kind of cameras. And we know that 3D cameras have different data formats, and we need to deal with that. Do you think that the 3D camera can help with the like more richer information in the rendering, or it's like?
So by 3D camera, you basically do you mean depth camera, or do you just mean the 2D cameras that are at different angles and give you the 3D information? Yeah. Uh-huh.
Use some algorithm to make it 3D. So
Yeah. So those are actually great for estimating depth. So depth is, like the way that our eyes do. You can tell how you use two different perspectives, and we have a sense of depth. So these cameras are used for depth perception, but for state-of-art 3D reconstruction is actually done the way I showed you. That's the best way. Yeah, exactly. Yeah. So even these cameras that capture from multiple perspectives, they're still just 2D. There's no fundamental way of capturing 3D. Yeah, it's always just 2D. Mm-hmm.
And maybe we later will involve processors, for example, the robotics.
Yes.
Is that for all of these type of data, like communicate or cooperate? Because now we see that, for example, one specific data has one specific like model or something.
Yes, that's actually one of the key unsolved problems, especially in robotics, how to do multimodal, like VLAs that take multiple inputs, not just vision. Yeah, so that's like a very hot area right now. That's a great point, yes. Yeah, exactly. Yeah, that's a great point.
The I just asked the same question.
That's okay. Yeah, I'll be here later also if you want to chat somewhere. All right. Yeah. Thanks, everyone. Yeah.
Thank you so much.
Yeah, thank you.
Yeah. Thank you for being here. See.